Hello, everybody. I'm Kereszturi from Hungary, from Europe. So thank you for this online option. What I'm going to talk about is an online IT application, let me say, which we call LungiStrat, which is an acronym for Lunar GIS for Stratigraphy. This is an open source web-based lunar ejecta thickness estimation and calculator tool, which is supported by the European Space Agency, the development, and mainly done by my PhD student, Richard Tomka, who is not here. I would like to give a short overview. How does it work? So it is about automatized ejecta estimation. Basically, it uses the known craters from the Robbins 2018 database, which contains about 2 million craters down roughly to 1 kilometer diameter. And we use the empirical-based ejecta thickness and distribution estimation method. So here you can see differently sized, smaller and down the larger craters. You can see the profiles here. The blue lines indicate the really measured profiles. The red one is the model calculated profiles. So it fits somewhere better, somewhere less. But anyway, so it works as an empirical ejecta calculation. Of course, we separate bedrock uplift nearby the crater and the ejecta itself. Here you can see some further examples. This is a part of the Artemis landing area, one of it. And here you can see the calculated thickness from the craters. Ejecta plus uplift, here only the uplift and here only the ejecta. So the ejecta is calculated for differently sized craters and then summarize all of the coincided craters. There are many drawbacks and weaknesses of the model. For example, distal ejecta is not properly handled, it is patchy, and so on and so forth, as you know. Just some further examples, how does it work? So you click somewhere on the moon, on a lunar map, or indicate the input coordinates numerically. Then the system evaluates the craters, actually all on the moon, which how far is it, the given crater, and what is the size. And based on the formula I mentioned in the last slide, would it provide ejecta to the given location or not? If provides, then calculates how much ejecta it provides. And from this, it is able to estimate the total ejecta thickness at the given site. Of course, this is a rough approach. Here some further examples demonstrate how the system works. If you click east or west toward east or west longitudes, then you can see if you approach certain craters, it provides much more ejecta, which is indicated by color shading, or less if you go further away from the crater. And after this, you need to provide an inferred subsurface stratigraphy, which is very difficult, of course. Two approaches we are using. The bigger crater is older, but it's a very funny approach. But what is more relevant, the more eroded edge crater is older and can be situated lower in stratigraphy. Here you can see some further examples. There is one paper which came out this year, and we are working on several more craters and the tool itself. We analyzed the ejecta thickness for an example Artemis site, considered only local craters above almost half kilometer diameter. You can see the coincided craters. Here you can see also two profiles with yellow. Along these profiles here, these two diagrams show the ejecta thickness in the vertical axis. And after this, you can identify various locations, for example, A, B, and C locations. And let's see what is the inferred stratigraphy at these locations. Here you can see at lower right, this is the crater degradation order-based stratigraphy. This is the crater size order-based stratigraphy. And the numbers mark the craters, certain craters, and the thickness is the ejecta that was that arrived to the given site based on the on the empirical approach. And you can estimate various interesting numbers. For example, there are two main craters which provide most of the ejecta. It is maximum 30 meters, or only from the coincided craters, not from larger, further away craters. But if they provide, and they did, these ejecta is below probably this top layer. And you can identify 7 superimposed ejecta layers if you are considering all the local craters. Here is the tool. How will it look like? It is working only personal computer yet, but we are aiming to release to the community. We will see when, hopefully next year. So it is the interface. It can be run from a simple browser window. You can click anywhere on the moon, on the lunar map, or give in the coordinates by numerically. Click, then the system calculates those craters which provide ejecta based on the database and provides some interesting output. For example, it indicates according to diameter and distance which craters provide ejecta, and provides also a table-based summary which can be downloaded as a CSV file. Here you can see as a CSV file. It gives the ID number, latitude, longitude, distance, diameter, and thickness from the given crater the ejecta has that you receive. And theoretically, it provides a stratigraphy, which is in the right. You might realize this is a fake stratigraphy, so it is an earlier one which had a minimal thickness value. In reality, it is not like this, and now it works much better. Here you can see, and this is actually a small, simple visualization. Sorry for putting this animation. This is a small one, and it shows only how does it work. You select a point on the moon. The system calculates depending on the computer, and then calculating for a few seconds, then identifies the craters which provide ejecta based on the approach. And at the bottom of the screen, you can identify which crater, how much ejecta provides, and at the bottom, the final result. Yes, so about the summary. So we are working to develop, to finalize this tool and release to the web. It will not be a simple click-based release because it is an ESA-supported project and we need to consider various aspects. But the final aim is to give to the community. And there is a wide range of possible future development we are already thinking about. It needs further verification, but the equation that calculates the ejecta can be modified anytime. It's difficult, but can be done. So it can be improved to provide better ejecta estimation. And we are running a service for Apollo 11 site. We're aiming to implement regolith properties. So there's a lot of possibility in the future, which is about our dreams, of course. So earlier it will be published at the beginning of next year. I wrote end of this year, but probably beginning of next year better fits the reality. And of course, we are searching for partners with WebGIS portals because we do not want to develop a WebGIS. This is a simple application, mainly Python-based, that can be implemented to already running WebGIS systems. And if you are interested in, just feel free to write me. Okay, thank you very much. That's all.
Any questions online? Not yet. All right, I've got a question while people can think of their questions. So I really like that you're planning on making it open source and available. Is this something that you think you'll have the resources to continually maintain?
Very good question. Of course, we do not have the resources to maintain for decades. We are now developing toward such an open source version, which can be handled by the community itself, and we would like to simplify during the server migration. There are two main topics that should be solved. First is the security from the server side. The second is we do not want that nobody wants to update monthly. So we would like to simplify the system. How could it be maintained? I don't know. it is the truth. I don't know, but we like this idea and we would like to continue further as it is possible, and would like to collaborate with WebGIS portals that might help in the maintenance aspect. And I didn't mention there is one more possibility. You are not only to use Robin's database, but you can upload your own crater counting and coordinate results. And in this case, the system calculates the ejecta only for those craters that you counted and uploaded as a simple CSV file.
Are there any other questions in the room? Any other questions online? Going once? Twice? All right, let's thank our speaker again.
Thank you very much.